Good day, grade 12 learners. Welcome to today's physical science lesson. My name is Mashudu Mamburu. This lesson is brought to you by the Gauteng Department of Education in collaboration with Saibono Discovery Center. As you can see, our topic for the day is photoelectric effect. So this is your last question for paper 1. So I'm hoping that we'll work through it and you'll gain even much confidence on the topic. If we look at the topic, it's part of matter and materials, that one, the last topic, which now has knowledge area has been given 15 marks. That is 10% of the paper. The paper 1 is still part of the whole paper that we are going to talk about. And then you know that paper 1, we have 20 marks multiple choice question. So you expect to find a multiple choice question based on photoelectric effect. And we have 130 marks. And total of 150 for paper 1, and paper 1 is still 3 hours. We always remind you this so that you get used to the structure of the prelim paper that you will write, as well as the final paper that you will be writing. Now, with no wasting of time, we'll go straight to the topic. However, I would like to first show you the prior knowledge to say you are not coming to this topic empty-handed. Remember, we're saying the topic is photoelectric effect. So in grade 10, you have done what is called electromagnetic spectrum, or what we call electromagnetic radiation. I think you'll remember that you were talking about the radio waves, the microwaves, the infrared, the visible light, the ultra visible light, the UV, and then you were talking again about X-ray as well as gamma rays. So those are the spectrum, the electromagnetic radiation. So these electromagnetic radiation were put in order of frequency and wavelength. Always remember the relationship between frequency and wavelength. I would like to start with that to say from the equation C equals to F lambda, you are able to see the relationship where C stands for the speed of light. Remember the speed of light, we're saying is 3 times 10 to the power of 8 meters per second, or you can just say 300 million meters per second. That is the speed of light. And then we talk about the frequency and wavelength. So the relationship between frequency and wavelength is that frequency is inversely proportional to wavelength. So frequency is equal to C over lambda. So it's important. So in other questions, you'll be given the wavelength. In other questions, you'll be given frequency. So you're able to calculate one from another by using this equation. So this equation is very central here because we're talking about light. This question is about light, and we're saying photo. Remember that the word photo stands for light. So we're going to do photo, which is light, electric, we're talking about charges. In this case, we're going to focus on electrons. So we're saying the topic is photoelectric effect, meaning that we're going to look at the effect of light on the electrons, how the electrons behave when they gain energy. So we'll be looking at that, which is something that we have started in grade 11, grade 10, when we were doing electromagnetic radiation. And we are saying we're going to look at the penetrating ability in relation to the energy and frequency. And when we're dealing with light here in this equation, is the particle nature of light. Remember, we talk about light having dual nature, which is it can behave as a wave or as a particle. So here we're looking at light as a particle. And then we talked about the concept of a photon. A photon, we are saying, is a packet of energy. So we're going to look at this packet of energy. Remember, 1 photon for 1 electron. That is the relationship that we must have as we lay this foundation to say if I'm coming with a photon or a packet of energy, 1 packet of energy will target 1 electron, which means I can be able to increase the number of photons, which we refer to as intensity. We'll talk about the effect of intensity, which is the increasing the number of photons per unit time. So we're saying we have these photons that are referred to as packet of energy. So you got to know that light has photons, and photons are referred to as packet of energy. So when we see light, remember, when we talk about light, we can talk about visible light. Visible light, you'll remember the visible light that we have. I think you remember the Roig beef where you had the red there, orange, yellow, green, and then the blue, indigo, and violet. So those are the colors that you will find on your visible light. So we'll talk about that as well. And then we are saying energy of a photon is given by the equation E equals to HF. So it's important to know this equation of E equals HF, which you have done in grade 10, and you'll be using it a lot in photoelectric effect. So it's very much important to look back where you started in grade 10 and we are building on that. So we are saying prior knowledge is very much important. Remember what I said in the beginning? I said frequency is the same as C over lambda. So sometimes you will be given wavelength. So you can use that equation HC over lambda, which will be able to give us energy. So there are two equations of energy that we are having. We're saying E equals to HF. When you are given the wavelength, you'll say E equals to HC over lambda. Remember, H is Planck's constant. So H is a Planck's constant, which is 6.63 times 10 to the power of minus 34. Is there in your data sheet. You will be able to be, is given. You don't have to cram it. It will be given on your paper. You'll be able to do that. C, we said it's a speed of light, which I said is 3 times 10 to the power of 8 meters per second, or 300 million meters per second. As well, C is given in your data sheet. So these are constants that are freely given on your data sheet, so you don't have to cram them. The only thing that you need there is a wavelength, so that you are able to calculate energy of a photon. So this is grade 10 work. This is what the knowledge that we expect you to be having now when we start with this topic. Now, in grade 12 now, we're introducing the topic now, that concept of photoelectric effect. So we're going to look at the effect of this light on the electrons, how the electrons are going to behave when they are bombarded with light of different frequency. Remember when you say light, we said light has frequency, and that frequency is given in terms of the energy of that light, which is HF. That frequency is the one that is going to determine how the electrons will behave when they are bombarded with light of that specific frequency. You will get that. So we're going to look at that. The first thing we're going to look at is the definition of photoelectric effect. Remember, for definitions, we are always using the exam guideline. I know as you are watching this lesson, you have the exam guideline before you. That is your friend. Two things that we are saying as in physical sciences. We are saying always exam guideline, always data sheet. So when you start a topic, you must know which data sheet applies to this formula. You will get the data sheet of wave, sound, and light. That's when you will get the data sheet for photoelectric effect. You must be having it before you. You must be having the exam guideline, so that when you do the definition, they are in accordance to the exam guideline. So three important definitions is photoelectric effect, threshold frequency, and work function. So you have to know those three. Already I've defined a photon for you to say a photon is like a packet of energy. So we're saying light has photons, and these photons are packets of energy. So all the time when you see light, you must know that light has those photons. Remember, I'm using the word light or electromagnetic radiation. So sometimes I'll refer to light, to it as light, or to it as electromagnetic radiation, but I'll be talking to the same concept. And they were saying these electromagnetic radiations, I indicated the radio waves up to the gamma rays. We are saying all of them, they have frequency. So we're going to have photoelectric effect, threshold frequency. Threshold frequency, we're going to define it as well. We're going to define the work function. So 4 definitions so far that you must always remember. And then we're going to look at the effect of intensity. Remember what I said? I said when you increase intensity, you are increasing the number of photons per unit time. So you must know all the time when you say we're increasing intensity, it means we're increasing the number of photons. Already I've clarified to you to say photons are packets of energy. So when we increase intensity, we're increasing the number of photons, which is the number of these packets of energy. So I want you to have this information before we even start with the topic, so that you are able to remember when we have to apply what I'm talking about. Now, why is photoelectric effect important in our daily life? Is there any applications that we use photoelectric effect? So we're going to look at the application of photoelectric effect. And then we're going to use the equation, this equation, which is E equals to the work function plus maximum kinetic energy, EK max. So we call this photoelectric effect equation. So it's the photoelectric equation that we are going to use, and then you must know it is E equals to work function. So already you know work function is given by that formula, and then by that W0. EK max is for maximum kinetic energy. I know already you know kinetic energy is half mv squared. You know that kinetic energy is half mv squared. The only difference was saying maximum velocity there that we are having. So it's important to know. Already I said to you that energy of a photon is E. So when you see E, you see energy of a photon, which in this case I said is equals to HF. So when you see E, you know that E equals to HF. You have a work function, which is the minimum energy required to eject electrons from metal surface. I'm going to give you all these definitions. I just want you to understand that these are the equations that we are going to use. And I said you can expand the EK max to be half mv squared. So you can write your equation of photoelectric effect as HF equals to work function plus half mv squared. Maybe you're asking yourself about this mass. It's a mass of what? Remember, we're talking about an electron, which means it's the mass of an electron, which in this case is a constant that is given in the constant table in your data sheet. So you are able to know that the mass of an electron you will be given. What you'll have to calculate is can be the speed of those electrons. So it's important that you remember this equation. We're going to explain it even much better during the lesson. But I wanted you to compare what you have learned in grade 10. In grade 10, you have learned E equals to HF. In grade 12, we're expanding that equation. We're saying E equals to W0, which is work function, plus maximum kinetic energy, which is given by that photoelectric equation that I've written there for you. So you got to see now we are moving, we're increasing. We are not saying E equals to HF only. We're saying that equals to the work function plus EK max. So know that formula that you'll be utilizing. I would like to start the lesson by looking at the objectives, meaning that at the end of this lesson, this is what you must know. So for us to say we're able to reach what we wanted to reach, you must be able to define photoelectric effect. You must be able to define work function. You must be able to define threshold frequency. So those are the three most important definitions that you must know at the end of this lesson. And I said to you as well, know what is a photon, which I said is a packet of energy. So those four things, the definitions, you must know them, you must sing them, because I'm saying to you, as you write your prelim exams, as you write your final exams, you will be able to ask those questions to say, define photoelectric effect, define work function, define threshold frequency. Now, you must be able to calculate using the photoelectric equation. I just introduced you to the equation to say the photoelectric equation is the energy of a photon equals to the work function. We said work function is the minimum energy required to eject or to remove electron from a metal surface. I'm going to expand on that so that you understand where it comes from, plus EK max. So that is the photoelectric equation that we are going to use. So you must be able to use it to calculate. So we'll do some calculations, we'll do some previous question papers so that you have a feel of how to use photoelectric effect equation to answer questions. I told you about the effect of increasing intensity. To say when we increase intensity, we're increasing the number of photons, which I said number of photons here, we're talking about the number of packets of energy. So you've got to know, we're going to look at how this increase in intensity going to affect photoelectric effect. And then we're going to look at the effect of frequency. If we change the frequency, remember we said energy of a photon is equals to HF. So if we increase frequency, what happens? What are the effect? What are the effect on the EK max and all that in terms of electrons? How will they that affect our electrons? How they will behave? We're going to look at that as well, which is effect of frequency. Lastly, is emission and absorption spectra. So say you must know the difference between that. You must be able to define that as well. So these are our objectives of this lesson, and you must be able to check at the end of this lesson. You must be able to say you know all that is in that. And if you know all this, we'll say you are ready for question 10 or for last question of paper 1 when you write your your exams. Now, we start with the definitions as I indicated. So we're saying photoelectric effect is the process whereby electrons are ejected, electrons are removed. Where do we find these electrons? We find them in a metal, from a metal surface. Electrons are removed or electrons are ejected from a metal surface. So we're saying you have your metal, let's say your metal is sodium. Remember the group 1 in the periodic table. If you want to see metals, you have group 1 metals where you will find your lithium, sodium, potassium. You have your group 2 metals, you will see calcium, magnesium, the likes. And you have your group 13 where you will find aluminium there. All those are metals. And then we're saying when the removal of electrons from metal surface, this on the surface of the metal, we're saying we have electrons. We are thinking here that in grade 10 as well, you have done bonding. Which you did covalent bonding. You said is the sharing of electrons. You have done ionic bonding, where you said in ionic bonding is the transfer of electrons. And then in this one, we're talking about metallic bonding, which you say is when a metal bond with another metal. Remember we said in metallic bonding, the electrons are delocalized, meaning that the electrons are delocalized around the metal. So you will be having a metal and then the electrons that are delocalized around it. So you have electrons that are there on the surface of the metal. So we're going to look at the effect of bombarding, or the effect of bringing in light here. When light is shown onto these electrons in the metal surface, the electrons are supposed to be removed, because we are saying electrons are ejected. What is photoelectric? We're saying it's a process whereby electrons are removed from a metal surface. So we're going to remove electrons from a metal surface when light of suitable frequency. The most important thing is not any light that you will show to electrons to remove them. It's only light of suitable frequency is incident on that surface. When the light is incident on the surface of a metal, the electrons will be removed. Then we call that photoelectric effect. Then we're going to look at when do we have photoelectric. Is that any light remove electrons? No, only light of suitable frequency according to this definition. So always remember the definition of photoelectric effect, which we are saying photoelectric effect is the process whereby electrons are ejected or removed from a metal surface when light of suitable frequency is incident on that surface. When light of suitable, because it's not just light, it's light of suitable frequency. It must be light of suitable frequency. So we start from the end when we define to say it is the removal of electrons. The removal of electrons when light of suitable frequency is shown onto this metal surface. So please remember what is photoelectric effect. Now, the next thing that you must know, remember we have two things. There are two things involved here. We're having light. I told you that we're going to refer to it as light or electromagnetic radiation. So we're having electromagnetic radiation. So we are saying electromagnetic radiation has energy, and that energy is called energy of a photon. So you have light that carries that packet of energy, or those packets of energy that it has. Now we are saying, now when we show this light, or when we bombard the metal surface, there will be, so we are saying there is a light, that the light itself, we are saying it has its own energy, which is given by HF, but we are having a metal here. The metal has work function. So the metal has work function. So there are two energies that we're going to compare. Is the energy of light versus the energy of the metal itself, which is the work function. So what is work function? We are saying work function is the minimum energy that an electron in the metal needs to be emitted from the metal surface. So the minimum energy required to emit an electron from metal surface. How much energy? So the metal has a price to say work function. For me, for you to remove my electrons, this is the amount of energy that you must bring. Hence, we are saying that energy, minimum energy required to remove an electron from metal surface, we call it work function. So there are two things that at all times you're going to compare. Is the energy of a photon, which is coming from the light, versus the work function. How much is the work function? How much energy is required to remove the electron? How much energy are you bringing to remove that electron? Will you be able to remove that electrons? Remember, if your energy is less than the energy of light or energy of a photon, if it's less than the work function or the minimum energy required or needed, then there will be no photoelectric effect. So it depends on that, how much energy you are bringing, how much energy are you bringing. If it's less than work function, there will be no photoelectric effect. But if the energy that you are bringing in is equals to the work function, let's just say they are equal, there will be removal of an electron from metal surface because you meet the criteria, you have the price, you are able to pay the price of removing that electron. So it's important that these two things, always you are looking at them to say how much energy do we have, how much energy is required, which we call work function. So if they are equal, they will be photoelectric. But we are going to have a last scenario where the energy of a photon is greater than work function, which means now it will be able to remove the electron, but the rest of energy, because now it's greater, when it's great, where will the other energy go? The other energy will be converted to kinetic energy. That's where kinetic energy is coming from. It comes from the rest of energy. When work function, when you have energy of a photon, having work function and extra energy more than the work function, then that other energy will be converted to kinetic energy. So what am I saying? In conclusion of this, before I move, I'm saying to you, there is always a condition to be met for the photoelectric effect to occur. The condition is that the energy of the incident photon must be equal or greater than the work function. If it's equal or greater than, there will be work function. When it's equal, there will be removal of an electron. When it's equal, there will be removal. When it's greater, equal, and more, then greater, it means that there will be removal of an electron and other energy will be converted to kinetic energy. So I think you now understand why we're saying energy of a photon is equals to work function plus EK max. Meaning that if this is 20 joules and the minimum energy required to remove an electron is say 15 joules, the other 5 joules will be converted to EK max. The other 5 joules will be converted to that. I think you get that. I've explained the concept to say there will be money there will be amount of energy that will be used to remove an electron from the metal surface, and that we said is the work function. However, we are saying that other energy will be converted to kinetic energy, which in this case, I said if we have 20 joules, energy of a photon is 20 joules, then if the work function minimum energy required to remove the electron is 15 joules, the other energy will be converted to kinetic energy. I hope you see how we are going to spend our energy. So all the time you check your budget to say how much do we have, how much do we need, and how much are we going to convert to other stuff. I hope you got that concept, and as we move, we'll be dealing with that kinds of questions. Now, as indicated, that we are dealing with electromagnetic radiation. So here we are dealing with your radio waves, where you listen to your radios, your microwaves, where you're using your microwave at home. I know you know the microwaves, the infrared, and the visible light. Remember, with visible light, I showed you that we're talking about the colors that you know, like red, your Roig beef. In the past, we were referring it to Roig beef, but with research, you can see that now we have another color that is cyan, but that is not important for this lesson. So what we have to know is that under visible light here is the colors that you can see with your eyes. And then we are referring here to your red color, your orange, your yellow, your blue, indigo, and violet. So those colors that we are referring as Roig beef or VIBGYO. And you can see that as we show that here, I have made a mnemonic here to say, just refer to it as Rami Fuchs. Remember, we don't want you to forget. We want you to always remember how this electromagnetic radiation looks like, the spectrum itself. It's Rami Fuchs. What are we saying? We're saying we have radio waves, microwave, we have infrared, visible light, which I said visible light. We have 7 colors there. Your red beam, and then we have the UV, ultraviolet light. Then you have your X-ray. When you have bones there, you can see that we're using X-ray. Then lastly, we have the gamma rays. Now, maybe we may have to look at the difference in terms of there are two things, which is frequency and wavelength. So you can see that as you move this side where you have radio waves, you have a longer wavelength. But as you move, remember, a longer wavelength means lower frequency. So you got to know when the other one, the relationship between frequency and wavelength is that when the wavelength is longer, the frequency is lower. When you have lower frequency, you have lower energy. Remember the relationship there to say energy is directly proportional according to this equation. Energy is directly proportional to frequency. So when the wavelength is longer, the frequency is lower, meaning that the energy here, you are expecting that we have lower energy this side. As you move here, the energy increases. So you can see gamma rays, lot of energy. That's why we're saying human beings, when they're exposed to gamma rays, they can have cancer and all that. So it's important when you want to look at the bone, you want the X-ray because it's a lot of energy that we have there. When you say we have higher energy, you are saying shorter wavelength. I'm able this slide because it's able to show you that the wavelength here, you can see how close our waves are. And then, but when you look here, you can see we have a longer wavelength. Longer wavelength means higher frequency. Longer wavelength means lower frequency, and then shorter wavelength means higher frequency. So I hope you had that understanding to be able to see that, okay, the gamma ray is the one with the highest frequency, hence the highest energy, and then as well as your X-rays and all that. Hence we are saying as well, don't be exposed to the ultraviolet because from the sun and all that, you are able to get that lot of energy. Hence you will use your spectacles and all that so that you are safe. So you are able to understand that. And then we look to, remember I said it's Rami Fuchs. I want you to have that in your mind. It is okay, our spectrum is like that, radio to gamma rays. Ne? And then we are saying now, V there stands for visible light, and visible light is what you can see with your naked eye. And you can see we have your red there, we have your orange, yellow, green, and all that, your blue and violet. So you can see these colors that are visible to our light. And then we're saying we refer to that as visible light. So in the question, we can give you any of the visible light to say a metal now is exposed to this light. Will there be photoelectric or not? Remember, these lights, they have their wavelength in nanometers. So you can see the red, it will have 625 to 750 nanometers, orange 590 to 625. So the wavelength there is given. And you know what does the wavelength higher, a longer wavelength, what does it mean? When the wavelength is longer, I've explained already, longer wavelength means lower frequency, which means lower energy. But shorter wavelength means higher frequency, and then higher frequency means higher energy. So you got to know the relationship between energy and frequency is directly proportional, but the relationship between frequency and wavelength is inversely proportional. So I hope you understand now the spectrum, the whole of it, including the visible light, because some of the questions you will see will be talking about these colors that you know, your everyday colors that you come across. Now, I wanted to include this one to say, let's look now when you have, say, your UV light that you are going to expose. So this type of an experiment that we are having to say, if we look here, we're having a metal surface. We're having a metal surface, and then you can see what happens when we expose the metal surface to the light. So we're having light here. You're having light here, and then our light is able to, if I can write here, we're having our light that we expose now the metal surface now. The metal surface there, when exposed to light, what happens to the electrons? The electrons now are being removed from the metal surface. So that's what we are referring to as photoelectric effect. So this is an experiment. I'm just using this GIF here to be able to show you how this photoelectric effect takes place. So we expose the metal. Remember I said the metal has work function. So we expect that we have a metal that has work function. We have light that has energy of a photon, which is HF. So those two things is E being compared to W0, which is work function. So you have the work function, you have the energy of a photon. So those are the two things that we are comparing. Now we are saying if is less, if the energy of a photon is less, there will be no photoelectric effect. But if it's equal, there will be photoelectric. Electrons will be removed, but they won't have kinetic energy. But if it's greater, you will say that there will be, if it's greater, there will be work function plus EK max. So this is the case that we are having in this one. You are able to see it now that when you expose, the electrons are removed. The other thing that I want to emphasize to you is to understand that our cathode here, with the issue of the batteries and all that you are able to do your connections and all that. So you can see that we have a cell here, and then we are having that happening. So you can see that is the cathode that we target. So we are showing this light to a cathode, then electrons are able to move from that cathode to that side of the anode. So you are able to see that experiment and see that what you can be able to define from this GIF to say, we are saying that it is the removal of electrons from the metal surface when light of suitable frequency is shown into it. So for photoelectric effect to take place, the light must be of suitable frequency. So you can see that this is light of suitable frequency. That's why there is the removal of electrons when light of suitable frequency is shown into it. So we can be able to change the light and use different lights or different electromagnetic radiation for you to be able to have the understanding. I think that has helped you in understanding the concept of this photoelectric effect. Then we're going to look as well to say, in our life, day-to-day life, where do we apply photoelectric effect? Is it working, or is just something that we're doing in theory, or is something that is important for us? So without wasting of time, I will just take you through some small history to say when metal surfaces are exposed to electromagnetic radiation with sufficient energy, they absorb the photons. Those packets of energy, the photons of energy that I referred to, they are absorbed. They are absorbed by the metal surface, or by the electrons that are found in the metal surface. So when electrons are exposed to these photons of energy, they absorb those photons of energy, and they are able to be released or emitted from the metal surface. And this is what we refer to as photoelectric effect. Now, I just want to tell you, this is just 3 bullets there to tell you where this all started from. It was Heinrich Hertz that was the first to discover this in 1887. We won't ask you questions on the history of how photoelectric effect happens, but I just wanted to give you a brief, just 3 bullets to say this is where we are coming from, because we appreciate science, we appreciate people who have made difference in the science that we are learning, because we always encourage you as well to follow science and do research and come up with even more things that we can be able to utilize. Now we are saying in 1901, Max Planck showed that energy is quantized. So you see, it's not only one person who contributed. Heinrich Hertz, most frequencies measured in hertz is from him. Now you have Planck now, who's bringing Planck's constant, the H there. The F, we are saying the frequency, the issue of frequency has to do with hertz. And then Planck is bringing Planck's constant and the energy of a photon, which is E equals to HF. So that which you have done in grade 10, it was about E equals to HF, which is the research done in 1901 by Max Planck. Now, this which you are doing in grade 12 has been done by Albert Einstein. who explained the photoelectric effect in 1905. So you can see Einstein there, who came up with this concept. And I want you to always, in your mind, to think of light. So we have light that has energy of a photon, and we have metal, in this case sodium metal, that were given there. And then we're saying this E, when you bombard or when it's exposed, you expose the metal surface to the energy, what happens? The electrons will absorb the energy from the photons, and then they will be removed if it's suitable frequency. Only when we have suitable frequency, we are able to remove that. So that is the research that was done by Albert Einstein. So what are we saying? We are saying electromagnetic radiation consists of small particles or packets of energy that we refer to as photons. So I want you to have an understanding to say we're talking about electromagnetic radiation, which I just showed you those many colors. I said it's Rami-Fuchs, so that you don't forget that, which is your radio waves, microwave, infrared, visible light, ultraviolet, X-ray, and gamma ray. We talked about the issue of the wavelength versus the issue of frequency. So we are saying EMR, or electromagnetic radiation, which are those 7 that we have there. We are saying they have packets of energy. These packets of energy are referred to as photons. Now, when you expose a metal surface to these photons, what happens is that these photons will carry energy which is proportional to its frequency. And then because metals, we said the metals are within delocalized or free electrons around them. It's very much important that you understand metallic bonding here to say the electrons, they are free electrons around what? Around a metal. So when you bring the light, when light is directed onto a metal surface, a photon will collide with a free electron. So what we are saying is that the electrons that are around, they will absorb the energy from the photons. Now what happens? The interaction between a photon and an electron is 1-to-1 correspondence. No, understand this. If you have one photon, you will only be able to remove one electron. So don't think that you can have one photon that will remove many. So if we increase the number of photons, the number of packets of energy, is only then that will remove even more electrons. So you will know that the effect of increasing the intensity, it means we are increasing the number of these photons. And when you increase the number of photons with relevant good energy or suitable frequency, they will be able to eject more electrons. So this is the question that we ask. So it's important that I emphasize it here to say when we increase intensity, we're increasing the number of these photons. And when you increase the number of these photons, you will be able to eject more electrons per unit time. Now, the photon can then be reflected without a change in its kinetic energy, or it transferred all its kinetic energy to the electron. I want you to understand that statement as saying we can increase the intensity or we can increase the number of photons. However, because they belong to one electromagnetic radiation or one light, maybe it's red or it's green, let's say it's green light or it's blue light. If you increase the number of photons, you are not increasing the energy that they carry. As long as they belong to the same light or the same electromagnetic radiation, if it's ultraviolet, all of them will carry the same amount of energy. Meaning that when you increase photons, EK won't be increased. They will have the same maximum kinetic energy. So remember, when you increase intensity, it will affect the number of electrons that are ejected. Intensity will affect the number of electrons ejected, but it will not affect the maximum kinetic energy of those electrons. So the electrons that are exposed to the same electromagnetic radiation will have the same maximum kinetic energy. So I think I've emphasized that, and it will help you when we do questions. You will be able to answer the questions relevant way of doing that. And remember, intensity will affect the number of ejected electrons. We can refer to them as photoelectrons. It will not affect the maximum kinetic energy of those electrons. The photons can be, okay, I said that statement. Now, further to finish this is to say if the energy gained is sufficient or enough the electron will be removed or will escape from metal surface, and this process is referred to as photoelectric effect. Remember, when I started the lesson, I've defined it. I'm emphasizing this so that you have a good understanding of what is happening during the process. Now, part of the energy gained by the electron is used to release the electron. I've said that to say the energy will release. If as long as they are equal, the energy will release the electrons from the metal surface, or we can say it will overcome the force of attraction between the electrons and the metal ions, and the rest as kinetic energy of the electron. I said that to say when you have energy more than the work function, we said some of the energy will be converted to maximum kinetic energy. Okay, and then we are saying the minimum energy required to reject or to remove the electron from metal surface is called work function. So I think the metal has an expectation to say to remove my electrons, you must have minimum energy required. So the work function belongs to the metal, and the energy of a photon belongs to the electromagnetic radiation or to the light. So light has energy. So light carries E, metal carries work function, and we are always comparing those to ensure that do we have photoelectric or we don't have. If energy of a photon is less, there will be no photoelectric. If they are equal, there will be photoelectric. But if it's greater, there will be a photoelectric effect. There will be removal of electrons. The other energy will be converted to kinetic energy. And we are saying the magnitude of this energy is a few electron volts, and the frequency of that correspond to this energy is the threshold frequency, which is our third definition. Remember, we said our definitions is photoelectric effect, is the work function, which is said is the minimum energy required to eject electrons from metal surface. Now, number 3, we're saying the third definition is the threshold frequency, which is the minimum frequency F0, just like W0. So it's no longer energy, but it's the minimum frequency required to eject electron from metal surface. So minimum frequency. So those are the 3 definitions that I think by now you are singing them. Now we are saying the relationship between the work function and the threshold frequency. You have to know that sometimes you'll be given threshold frequency and then it will ask you to calculate the work function. So you must be able to know that when I want the work function, I can use HF0. I can use threshold frequency to calculate work function. How do you do that? You multiply threshold frequency by Planck's constant. Remember Planck's constant? We said it's a constant which is 6.63 times 10 to the power of minus 34. So you just multiply that by threshold frequency, you are able to determine the work function. So that is one of the questions that you will expect in the papers, questions that we're going to do. Electrons are only emitted if the frequency of radiation is greater than the threshold frequency. I've indicated there that we will always be able to see that when energy of a photon is greater than the work function, there will be removal of electrons, and some of the energy will be converted to kinetic energy, like that. The condition there is that HF, which is E, energy of a photon, must be greater than the work function. So you got to always be able to refer to that to give you the right thing. As we move now to do calculations, because I've taken you through all the scenarios so that you understand this topic. To say now, for these calculations, we'll be using what is called photoelectric effect, which in this case, we said photoelectric equation is the energy of incident photon, which is equal to work function plus maximum kinetic energy. So that is what we gave you. Energy of a photon is equal to the work function of the metal plus maximum kinetic energy of released electrons. So you got to know this for released electrons. And then as indicated, that energy of a photon is given by HF. And then we have our work function plus EK max. You know maximum kinetic energy is the same as half mv squared max. So you're able to know that you can be able to, the mass is there, is the constant there. So that is another equation where HF we said is the energy of a photon, W0 is the work function, half mv squared is the maximum kinetic energy of the emitted electrons. Why is photoelectric effect important? Why are we doing what we are doing, sir? We're doing what we're doing because we want photoelectric help us to explain the particle nature of light. Remember, we said light can behave as a wave and light can behave as a particle. So this question, which is question 10, the last question of your question paper in paper 1, photoelectric effect, we are saying this question, it helps us to explain the particle nature of light. And it is used as the basis for quantum theory. And as well, it's used as a photocells. Calculators that you use, solar calculators, they use the photocells. They were applying photoelectric effect there. The alarm system that they are using photoelectric effect. Automatic doors, when you move towards the door is opening, all that they are using photoelectric effect. So you can see that we apply photoelectric effect in our day-to-day living. So it's important that you know photoelectric and you know why we do what we're doing. Why are we doing photoelectric effect? Now, as I indicated, we're going to deal with that, which is the equations, the data sheet, and then with no wasting of time, we are going to look at how the electrons absorb this photon. So we're saying an electron can only absorb one photon. I've indicated that the relationship is 1:1. One photon will eject or remove one electron. So for the electron to be removed, it must first absorb the energy. So when energy from light, from electromagnetic radiation is shown, or when a metal now is exposed, a metal surface, the electrons will absorb the energy. When it absorbs the energy, it becomes excited, then it becomes to move, and then it is removed. And I've told you the condition of removal. So we're saying one electron can be removed by one photon, 1:1. Don't forget that. And we said the photon is given by E=hf. And we are saying if energy of a photon is greater than work function, if its energy of a photon is less than work function, there will be no photoelectric. So there will be no electron that will be ejected. I've explained that in many terms. We said when energy of a photon is equal to the work function, photon will be absorbed and the electron will be ejected, but there will be no EK or kinetic energy. But when it's greater, there will be excess energy will be converted to kinetic energy. Then the electrons will have to move using that kinetic energy. Now, for calculation sake, you know that A=hf, which we've done in grade 10. You know that A=AC/lambda, where we said E is the energy of a photon in light with frequency f and wavelength. That is wavelength, and c is the speed of light, which you said is 3 times 10⁸ meters per second. And then we have the photoelectric equation that I just explained. So this slide is just clarifying that to indicate that you will always as well compare F to F0. In a case where F equals to F0, then you know that the energy of a photon will be equal to the work function. So energy of a photon will be equal to work function when the frequency of the incident is equal to that, and then further explanation as we move there. So the brightness and energy. It's important that sometimes in the questions we'll talk about the brightness to say this is bright and all that, comparing a brighter light to a dimmer light with the same frequency to say brighter light contains more photons. So know the language. When you say a much brighter light is used, you know that we've increased the intensity. So you got to understand that when you increase intensity, more photoelectrons will be ejected per second. Now, same frequency photons has the same energy. So I've said this, and each photon electron has the same kinetic energy from bright or dim light. Remember, when it's dim, what we are not changing the EK there. So just showing that there is no effect on EK, but there is effect on the number of electrons, because I indicated that increase in intensity will change or will increase the number of photoelectrons that are ejected or that are removed. So it won't change the EK. So you got to have that in mind all the time. Now let's look at a graph, because you'll get some of these questions in graph form. like that to say light of different frequencies shown onto a metal, and kinetic energy of the photoelectron is measured for each frequency, and then EK is plotted against F. So you can see this is the graph of EK against F. You will see when you open a previous question papers, you'll get a lot of this type of questions. Now you must see that this is straight line graph, and we are saying it intersect on horizontal axis. EK equals to 0. You can see here where it intersect, EK equals to 0, and you know that this shows that when EK equals 0 shows that this is the value of F0. So threshold frequency where the EK, when EK is equals to 0, it means that energy of a photon is equals to work function, and then you know that the work function is HF0. Yes, so you are able to see that, okay, when we have that case there where EK equals to 0, we have F0. So on there, you know that this is the threshold frequency. Now, the gradient of graph is H. So when you have, remember, a gradient is change in Y over change in X. So that is change in EK over change in frequency there. That must be able to give you Planck's constant. So the gradient of this graph is Planck's constant. You'll get questions that will ask you, what is the gradient of this graph? You must be able to know that the gradient of that graph gives you what we call a Planck's constant, which is H. Now, the number of electrons emitted when the frequency of incident photon is greater than threshold frequency, then we'll have the electrons that are being ejected. Now, effect of intensity and frequency, I've indicated that the increase in intensity, the number of electrons emitted per unit time is proportional to the intensity of the incident light. So when you increase intensity, you will increase the number of electrons or photoelectrons that are emitted per unit time. So electrons emitted per unit time will increase when you increase intensity. Don't forget, when you increase intensity, you will increase the number of electrons that will be emitted per unit time. What is the effect of frequency on photoelectric effect? We are saying the maximum kinetic energy of the photoelectrons is linearly proportional to the frequency. So when we increase frequency, it will affect EK max. So you got to know that when you increase the frequency, the rest of that energy will be converted to kinetic energy. So this is what will affect EK max, not intensity. Intensity affects the number of electrons that are ejected. So I hope that will help you now as we start dealing with questions, activities. Now we're going to do previous questions and be able to see what type of questions we have to deal with here. Now we are saying the work function of potassium. This is a group 1 metal. Remember, in group 1 we have what I refer to as LINAC, which is your lithium, sodium, and potassium. So those are group 1 elements. So they are metals. So it's a metal. It has a work function. So we're given potassium. And its work function as 3,52 times 10 to the power of minus 19. So this potassium is said, for you to remove my electrons, the energy that you must bring, it must be 3,52 times 10 to the power of minus 19. So that is the work function, which is the minimum energy required to remove the electrons from metal surface. Now, an electromagnetic radiation, EMR, strike on the surface of the metal produces photoelectric effect. So they're saying photoelectric effect will take place. That statement is saying to you that the energy of a photon is greater than work function. So you know that you have more energy. The energy of a photon will be greater than 3,52. So now the maximum kinetic energy of the electrons ejected is 4,20. So you are able to see now that from the equation of photoelectric effect, which is E equals to work function plus EK, remember, you always remember that, we're given this as 4,20 times 10 to the power of minus 19 joules, and we're given the work function as 3,52. So if you add those two, you will be able to determine the energy of the photon. So this is what we are given. Now let's go to questions. define work function. So that is the first question. So you are able to define work function as the minimum energy required to eject electrons from metal surface. So that is the definition. Minimum energy needed to eject an electron from metal surface. So I hope you will know these definitions, because definitely we'll have that 2 marks of defining. Define photoelectric effect. It's important that we do all the definitions when we start with this lesson. To say photoelectric effect, we're saying is the process whereby electrons are ejected from a metal surface when light of suitable frequency is incident on that surface. So these are definitions from the exam guideline, because we are always saying to yourselves, do them according to exam guideline. I'm going to take a pause on this question, then I'll give you just a 3-4 minutes break so that you answer these 2 questions. Question number 1 is saying calculate the frequency of an incident radiation. So I want you to do that. Calculate the frequency of incident radiation. Remember, always go back to given information. You are given EK max as 4,20 times 10 to the power of minus 19. You are given a work function as 3,52. Now the question is saying calculate frequency. So already you will be able to know that frequency, we know that energy of a photon is the same as HF. So you have HF equals to that. Then you are able to substitute that and that. You know H as our Planck's constant. So the question is saying calculate the frequency. So you are able to calculate frequency. I hope you will do that question. When we come back, we'll do the question. The next question is saying calculate the wavelength. Remember the wavelength, you have C equals to F lambda. If you know the frequency, you can be able to calculate that. So I'm giving you the clue, but I want you to do the question and use your calculator and be able to be confident that you are able to do this question. So I'll just take a small, just 4 minutes. Then in 4 minutes time, you must be done with this calculation. We'll do the solution and move. Thank you very much. Welcome back. Hoping that you have enjoyed doing the activity. As I indicated, that the H was given, which is a constant 6,63 times 10 to the power of minus 34. We were asked for 1.3.1 to calculate the frequency. Work function 3,52 times 10 to the power of minus 19. And then EK max was 4,20 times 10 to the power of minus 19. So all you had to do was to substitute that and H and look for frequency. Obviously, we will divide both sides by H, which is Planck's constant, which is 6,63 times 10 to the power of minus 34. Then you are able to get your frequency. You have the wavelength of incident. You know that if you say C equals to F lambda as well for 1.32, it will help you because you know this is 3 times 10 to the power of 8 meters per second. The frequency is what we calculated here. You are able to calculate the wavelength. I hope you did those questions correct and you are able to mark yourself, and then you get all your marks there. So you wrote the equation, and then we'll give you 1 mark for one of the two, whether you wrote it like that or like that. We'll give you 1 mark for that. Then you are able to substitute the given work function and the given EK max, and then H, which is Planck's constant. You divide both sides by Planck's constant. You are able to get your answer there. So you can get your nice 4 marks there for that particular question. For the last question, now because you have frequency, we are saying now you can be able to calculate the wavelength. C equals to F lambda. You're able to write it as your equation. Then you get 1 mark for the equation. Just to copy it from the data sheet, you are able to write this is 3 times 10 to the power of 8. This is you carrying it from there. You get your frequency. You're able to substitute it there. Then we give you another mark for substitution. Then you calculate wavelength by dividing both sides by 1,16 times 10 to the power of 15, and you're able to get your wavelength as 2,59 times 10 to the power of minus 7. Hoping that you were able to do that calculation. Then you got all your 7 marks, and then you are celebrating. Remember, these are coming from previous years' question papers, so it's important that you have that understanding. Now, that question that I told you about, remember I talked about the effect of intensity and the impact of the effect of frequency on this equation that we're dealing with. Now, if you look, we're saying the intensity of the incident radiation on the metal plate is increased. I said it already that when you increase intensity, you are increasing the number of photons. And when you increase the number of photons, you are going to increase the number of ejected electrons or emitted electrons per unit time. Now, constant frequency. Remember, I indicated that frequency will affect EK max. Intensity will affect the number of electrons that will be emitted. So it's very much important to know that when it comes, as long as the frequency remains the same, the kinetic energy will remain the same. So there will be no effect in terms of kinetic energy because it's only frequency that affects the energy. Now, when it comes to the number of photoelectrons emitted, yes, when increase intensity, the first condition, I want you to have understanding here to say for the effect of the effect of intensity on the number of photoelectrons emitted per unit time, you look at this. You look at the energy of a photon. Was it greater or equals to work function? When it's greater or equals to work function, you know that the electrons were going to be ejected. If it's greater or equals to, you know that the electrons will be ejected. So if it's greater, it means electrons will be ejected. And if electrons are ejected or removed, then when you increase intensity, you will increase the number of photoelectrons emitted per unit time. So this must increase when you increase intensity. So I think you've understood that intensity affects the number of electrons that are emitted, but intensity does not affect kinetic energy. Kinetic energy is affected by frequency, but in this case, we said frequency remains the same. Hence, we are saying that if frequency remains the same, kinetic energy will remain the same. I hope 1.4 helps you to understand the effect of intensity as well as the effect of increasing frequency or frequency remaining the same. Now, a question paper from May, June last year, 2023. We're given a nice graph there already. We gave you a graph we told you have the graph of maximum kinetic energy versus frequency. We have shown you threshold frequency or cutoff frequency. Remember, we said when Ek max equals to 0, we have F0. So you can see that for this metal A, the threshold frequency is given as 5 times 10 to the power of 14. So I would like you to be able to analyze the graph before you even start to answer the question, to say the first thing that you know is that when we are given a graph of maximum kinetic energy versus frequency, we know that the threshold frequency is that one. The next thing that we talked about was the gradient of that graph, which is changing Ek max over changing frequency. Remember, we said the gradient of this graph will give us Planck's constant. So it's important that you have that information as information that you have before you start answering graph related questions. Now, we are saying here, in a photoelectric investigation, light of different frequencies was radiated on each of two metals. So we have two metals, but the graph is only showing metal A and metal B. The graph of the maximum kinetic energy of the ejected electrons from metal A and the frequency of the incident photons is shown below. So you can see there, then as the frequency is increasing, you can see the kinetic energy, what is happening, it increases. Remember the relationship, we said frequency is the one that can affect kinetic energy. Now we can see that as the frequency, as we move this way, the frequency is increasing. As we move to the right, when the frequency increases, you can see Ek max as well increases. Remember we said linearly proportional. They are proportional, the frequency and kinetic energy. Now, point X on the graph represents the maximum kinetic energy. So maximum kinetic energy is represented by point X there. And then let's go to questions. I've analyzed it for you to say, write down the numerical value of the gradient of graph P. Numerical value of the gradient. So you got to know that the gradient of this graph is Planck's constant. So the numerical value will be Planck's constant, which is 6,63 times 10 to the power of minus 34. I hope that helps you to always know that on this graph, the gradient is Planck's constant. So if you say calculate gradient, it must be able to give you Planck's constant, which is 6,63 times 10 to the power of minus 34. Now, for 2.2, we're saying define the term work function. Hence, I've emphasized that these four definitions that we did are the ones that you will be asked in this question. In 2023 May-June exam, they were asked to define the term work function. And we said this is the minimum energy needed to eject an electron from metal surface. Remember, electrons, we said they are in the metal surface. And when you eject electrons, you are ejecting them from metal surface. Then you are able to write the minimum energy needed to eject an electron from a metal surface. So you're able to get your 2 marks there for defining the term work function. So these are nice questions, and we are expecting you to collect as many marks as possible from these questions. Look at this one. The first question there is saying calculate the work function of metal A. It's very much important to know that now your data will be given on the graph. Metal A, you know work function, we said is W0 HF0. So you need what is referred to as threshold frequency, which we said threshold frequency is when Ek max is 0, which is 5 for metal A. So you are able to see that for metal A, that is 5 times 10 to the power of 14. So you know that this is H, which is 6,63 times 10 to the power of minus 34. You multiply that by 5 times 10 to the power of 14. Then you are able to calculate your work function, which in this case must be in joules. Remember, it's energy, and energy is calculated in joules. So you are able to do that, which is your 6,63 times 10 to the power of minus 34 times the 5 times 10 to the power of 14. This is the power. And then we are saying that gives you 3,32 times 10 to the power of minus 19 joules. So you are able to get your answer like that. I hope now you know how to calculate the work function, because we'll get many questions that want you to calculate the work function. Now, if we move now, or what is for 4 marks now, you have to determine the value of X shown on the graph. So you know X is kinetic energy. So you must be able to calculate the kinetic energy there. So if you think, you will think about the equation that you can use. You see that for that maximum kinetic energy, frequency is 12,54 times 10 to the power of 14. So you know that when you have frequency which is 12,54, you have HF, which is Planck constant, times F, which is your 12,54. Then you are able to write your equation as the work function. You calculated the work function as 3,32. So you are able to calculate, to put your 3,32. Then you can be able to calculate the EK max here, which will be equals to HF minus the work function. So you can see that these questions, as long as you have the understanding, you are able to do the calculations with no problems. So I was referring to the second option there to say you can be able to utilize the given information, which is HF, your Planck's constant, and your frequency, which is 12,54, and then you are able to write your EK max there, and then you are able to do your calculations. You're able to write your work function there, and then you're able to do your calculation of EK max, which in this case is 5 times 10 to the power of minus 19 joules. However, you can do the gradient, because you know the gradient, which is Planck's constant, which is h, which is given by x minus 0, and then you can do the change in f frequency there. Remember, final frequency was 12,54 on the graph. If I might just go back, the final frequency was 12,54 times 10 to the power of 14. The initial frequency was 5 times 10 to the power. So the change is always final minus initial. Remember, the change in y is your final, which is x minus 0. The change in x, it will be 12,54 times 10 to the power of 14 minus 5 times 10 to the power of minus 14. So you can use that as well to calculate, or you can easily use the equation. All of them, they will lead you to the answer, and then you are able to get your 4 marks, whichever option you chose to use. Now, as we move, we are able now to say now we have we got the value of, we got the question here. Just bear with me. The question here was, how will each of the following be affected if light of frequency 2,54 times 10 to the power of 14 hertz, but of higher intensity? So they're saying if we increase intensity when the frequency is 12,54, if we increase the intensity, how will that have effect on X? X is EK max. So on the song that I've been singing since we started with the lesson, I indicated that when we increase intensity, it has no effect on kinetic energy. So there will be no effect, because we said intensity will affect the number of photoelectrons emitted per unit time. So there will be no effect on EK max. However, what will be the effect on photoelectrons emitted per unit time? Yes, when increasing intensity, you will increase the number of photoelectrons emitted. So you can see that these things that we are doing, they are things that are asked in the exam paper. This was your May-June paper for 2023. Now they talk about another metal now that is the larger work function. Remember, larger work function means larger threshold frequency, because work function is given by HF0. So immediately when you say larger work function, remember H remains constant, which means we are increasing F0, or threshold frequency. So threshold frequency for B is greater than the one for A. That's what that statement means. When it says metal B has a larger work function than metal A, it means that now the threshold frequency of B is larger than threshold frequency of A. So it means you are expecting the movement to the right because it's a larger value. And then the question says, redraw the graph above in your answer book. Do not include values on the axis. Label these graphs A on the same graphs as A. On the same set of axes, sketch the graph for metal B. Label this graph as B. So for 2 marks. So you can see that already you are drawing the same graph, which you can just draw the axis like that. You knew that for A it was 5 times 10 to the power of 14, but for B now we are saying because the work function is larger for B, the threshold frequency will be larger, meaning that you have a larger one. So you expect B to be somewhere like that. So you are able to draw your graph on the same set of axes, and then you can show your EK max here. You can show your frequency this side. They said you don't have to show the values. We just wanted to see how will the graph shift when we increase work function, we increase the threshold frequency. Hence the graph B will be on that point. Then you are able to do that one. Now, let's look at another question, activity 3, another question paper. Remember when I started, I indicated that there are experiments that we deal with here, and we're dealing with this question of, I want to say, don't panic when you're dealing with this type of equation where we have a direct current source here in the experiment. What does this mean? It means that we are having a cathode here and the cathode. So panic means positive is anode. Remember the positive is this bigger one. So the positive side here we have the anode, and on the negative is cathode in this case. So the negative is cathode, meaning that the negative side is this side. This is our cathode. So you got to know that it is the cathode. We show the light, or we expose the metal on the cathode to the light. Then there will be, you will see that when incident light is shown into the cathode of the metal or into the metal surface, what happens is that electrons are removed. You can see they are moving from cathode to anode. So that is the experiment that you get. So you got to understand this experiment for you to understand this type of question. So we're saying now our positive anode, so the positive anode is this one, and negative is cathode. So this is our cathode. When light, light comes with a present, which is a packet of energy. The light doesn't come alone. When you have visitors, some they come with nothing, but light, when it comes with a packet of energy that we call a photon. So when light is when a metal surface is exposed to light, incident light, we are saying now that the electrons here on the cathode side will gain or will absorb the energy. And when they absorb the energy, because the energy is greater than the work function, then the electrons will be ejected. Hence, you see the electrons moving in that direction. I hope you understand this experiment. And when you see it, you will always have an understanding. Don't forget, don't panic. When we say don't panic, we're saying you just look for the positive. That is your anode. The negative, that is your cathode, then is able to help you to understand and answer the questions. Always we'll start with definitions. I think this is another question paper. It might be a 2022 May, June again, previous question paper, because we want you to have that feel of how the questions are asked in the exam. Now, define the term photoelectric effect. So remember, we said it's the process whereby electrons are ejected from a metal surface when light of suitable frequency is incident on that surface. So you can see every question paper, we are asking those 3 definitions: photoelectric effect, threshold frequency, and work function. So know those definitions, sing about them. The packet of energy, which we call is a photon. So you know that for this question, you will have 2 marks for the definition. Now, on the statement, we are saying incident light of frequency 1,2 times 10 to the power of 15 hertz. So you are given frequency, the F is given, or is shown onto a metal plate, and electrons are emitted. So already when you see frequency, you know that E equals to HF. So you know that you can be able to calculate energy of this photon because F is given. When F is given, you're able to calculate the energy of a photon. And they are saying electrons are emitted, which means this value of E is greater or equals to the work function. So that is what you'll get from that information. The first question is saying there, calculate the number of photoelectrons emitted in 1 second if the total energy transferred by the light to the metal plate per second is 1,75. So the energy that is given there was 1,75 times 10 to the power of minus 9. Look, that question has has 4 marks. And 3.1.3, which is the other question, it needed you to calculate the maximum speed of the photoelectron. So you see now, you are able to know that to do that question, you will have to have your equation as half mv squared, because now we want maximum speed. So the mass of an electron is constant, so you just have to calculate your E, your work function, and your mass, and then you are able to do your question. And look at the number of marks that are given for that particular question. We had 4 and 5 marks, which is a total of 9 marks. So you know that for one electron to be ejected, we have F, as I indicated, that when the Planck's constant is a constant, then we are given the frequency of 1,2. So you are able to calculate the energy of a photon. And when you know the energy of a photon, we're saying the number of electrons are equivalent to the number of photons. Remember at the beginning of the lesson, I indicated that one photon will eject one electron. So if you want the number of electrons that are ejected, it's simple as find the number of photons, because when you know the number of photons, is equivalent to the number of electrons, because one electron is removed by one photon. So what happens is that the total energy of photons, it was that 1,75 times 10 to the power of minus 9, and then the energy of one photon that we calculated there was 7,96. So it's total divided by 1, which gives us 2,2 times 10 to the power of 9. So at the end of the day, we know the number of electrons is 2,198 times 10 to the power of 9, or 2,2 times 10 to the power of 9. Those are the number of electrons, because we are saying the number of electrons are equivalent to the number of photons. Now on the last question, we were expected to calculate the maximum speed. And going to our equation, we were given our energy of a photon, which we calculated there as 7,96 times 10 to the power of 19. We use what is referred to as positive marking to say the answer that you got there for energy of one photon, it is the one that you do there. So it's important that you are able to substitute energy of a photon, and then you know Planck's constant is 6 times 6 to the power of minus 34, and then the threshold frequency is 9,09, and then you have energy, the mass of an electron is 9,11 times 10 to the power of minus 31. This is important because you are getting it from the constant in your data sheet. So the mass of an electron is a constant, Planck is a constant, the rest is what we are given. You are able to substitute. Then you are looking for V squared, so you are able to take the square root, then you get your V max as 6,51 times 10 to the power of 5 meters per second. Then you got your 5 marks and your 4 marks. So it's important that you practice as many, because you have access to question papers. Do as many question papers as possible of this type of questions. Now, our last question for the day is activity 4 as well, which is saying in the diagram below, in this side is the diagram aside. On this side, we are having green and blue light. Remember, we said we can expose them to this visible light. It's a visible light, which you said we have your red, orange, yellow, blue, green, all these colors. So we are having green light with a wavelength of 500 nanometers. We are having blue light with 400 nanometers. Remember, learners, we said immediately when you have wavelength, you know that E equals to HF, and you know that E equals to H. Frequency is the same as C over lambda. So you know that if you have wavelength, you know the energy of that photon, and you can calculate the frequency of that, because frequency was saying C equals to F lambda. So C is 3 times 10 to the power of 8, and wavelength is given as 500 nanometer for green light. So you can be able to calculate the frequency of this light. So it's important with all the given information that you are able to utilize it to your benefit. So the same here, you can say E equals to HF, and we know that E is the same as HC over lambda. and lambda is given as 400 nanometers. Don't forget, you go to how to convert nanometers to meters, which is times 10 to the power of minus 9. If it's macro as well, 10 to the power of minus 6. Pico, 10 to the power of minus 12. So those conversions become very much important, because we don't want you to lose marks because you can't convert to meters, because we use meters as our unit there. So you can't say nanometers. You must say 500 times 10 to the power of minus 9, 400 times 10 to the power of minus 9 for blue light. So those lights are given like that, and you can be able to utilize that information that you are given to calculate all that. Now, what property of light is illustrated by the photoelectric effect? Remember, we said light has dual nature. Light can behave as a wave or as a particle. So in this case, we're talking about the particle nature of light. So the answer to that is a particle nature of light. And then we're saying, without any calculation, give a reason why maximum kinetic energy of ejected electrons using blue light is greater than that obtained using green light. Why will blue light have more electrons ejected? Remember, we said shorter wavelength means higher frequency, and higher frequency means higher energy and frequency are directly proportional. So you're able to look at that relationship to say, okay, shorter wavelength means higher frequency, which means higher energy. So blue light has a shorter wavelength, meaning that it has higher frequency, and if it has higher frequency, it has more energy as compared to the blue light. So you're able to respond to that question. The wavelength associated with the cutoff or threshold frequency of a certain metal is 330 nanometers. So you are given 330 nanometers as the wavelength. Calculate the work function of that particular metal. And then for 4.2.2, we're saying calculate the maximum speed of an electron ejected from the metal surface when light of frequency 1,2 times 10 to the power of 15 is shown onto that particular metal. So you are able to do your calculations and then be able to answer the question. I have answered that one to say the particular nature of light, and we said when they have shorter wavelength, it means we have higher photon of energy, and photon energy is inversely proportional to wavelength. So meaning that I explained that to say when you have a shorter wavelength, you have a higher energy because of the relationship there. And then I'm able now to take you to the calculations. The first one, you were supposed to calculate the work function, which is now that given wavelength of 330 times 10 to the power of minus 9. HC are the constant, so you're able to do that. And then you just substitute. H is 6 times 6 to the power of 3, 6,63 times 10 to the power of minus 34, and speed of light C is 3 times 10 to the power of 8. The wavelength associated with the threshold frequency, it was 330 times 10 to the power of minus 9. Then you are able to calculate the work function, which is 6,03 times 10 to the power of minus 19. For the last part of the equation, you know that C equals to F lambda. Then you are able to say 3 times 10 to the power of that. Then you are able to calculate the threshold frequency. That's option number 2. So you are able to use that option to say, okay, I can use the wavelength in order for me to calculate the threshold frequency. And then when you get the threshold frequency, you can use it to calculate the work function, and still you are able to get your answer there. So there are 2 ways there that you can answer that question. For 4.2.2, we are saying already you know your equation that you are given there. For option number 1, you had your energy, which is HF, which is your Planck's constant times the given frequency, which is 1,2 times 10 to the power of 15. And then you had your work function, which is 6,03 times 10 to the power of minus 19, plus your mass of an electron, which is 9,11 times 10 to the power of minus 31, and you have your V squared. Then you take the square root, the mass part, then you get your V, which is 6,5 times 10 to the power of 5 meters per second. There is another option that you can use. What I would like to say now is to say the importance of data collection. Always do that, because when you collect information that you are given, you will be able to know what you have to calculate. And we are saying do as many calculations as possible, so that even the calculator skills are important here, because we don't want you to lose marks because you don't know how to use the calculator. So don't wait until it's too late to practice calculations. As of today, before you sleep, do as many calculations as you can, and you will be able to cover all that we have to cover. And when I finish, Albert Einstein, the one who dealt with this topic of photoelectric effect, is saying to you, anyone who has never made a mistake has never tried anything new. So let's keep on trying as many questions as we can, practicing as many questions as we can, and we are saying success is within our reach. So I would like to say, till we meet again, thank you very much for watching this lesson. Goodbye.